Hey everyone, welcome back to the Deep Dive. Today, we're going to be looking at something that sounds, well, really simple actually. The two pointers technique in algorithm design.
Oh, yeah.
But you wouldn't believe how much you can actually get done with this.
Yeah, it's surprisingly versatile. You can use it to really streamline a whole bunch of algorithms, make your code much cleaner and more efficient.
I'm intrigued. I'm also a little intimidated. I know we're going to be covering a lot today. Things like the classic two-sum and three-sum problems. We're going to be working with linked lists, even sorting algorithms like quicksort and merge sort.
Oh, wow.
Where do we even begin?
Well, I think let's start with the core concept. The basic idea is that we're using two pointers to navigate through our data.
Okay.
And a lot of times this is going to be like an array or a linked list. So by strategically controlling how these pointers move, we can unlock some really elegant solutions.
Okay, I think I'm following so far. So we've got these two pointers. But what are they doing? Do they both move at the same time?
Yeah. That's a great question. Think of it this way. You often have a fixed pointer, and this is acting as like an anchor, defining a range or a boundary.
Right.
And then you have a floating pointer that does the heavy lifting, right?
Right.
It's actively like searching or modifying data within that boundary. And the real magic happens when you define the rules for how that floating pointer moves. Does it increment? Does it decrement? Or maybe it even jumps based on certain conditions.
So it's almost like we're playing some kind of strategy game, right?
Right.
We're setting up these pointers and then figuring out the best way to move them around to get what we want.
Exactly. And the beauty of it is it often avoids brute force solutions.
Yeah.
So instead of just blindly checking every single element, we're using these pointers to intelligently narrow down the search space.
That makes sense. So it's not just about speed, it's about like working smarter, not harder.
Exactly.
Can we see this in action with a real example?
Absolutely. Let's take a look at the classic two-sum problem.
Okay.
So you're given an array of numbers, and the challenge is to find two numbers within that array that add up to a specific target value.
Okay, I think I remember hearing about this one.
Oh.
And I think there were a couple ways to solve it, right?
There are. So one approach uses a set. You basically iterate through the array, and for each number, you check if it's complement,
Right.
which is the number needed to reach the target, right? It's
Right.
already in the set.
Okay.
And this is pretty efficient with the time complexity of O(n), meaning the time it takes scales linearly with the size of the input.
Hold on, time complexity. Can you remind us what that big O notation means? I always get a little fuzzy on the details.
Of course. Time complexity is just a way for us to express how the performance of an algorithm changes as the amount of data it processes grows. So big O notation gives us a simplified way to describe this growth.
Okay.
So for example, O(n) means that the algorithm's runtime increases proportionally to the size of the input.
Right, so if you double the input size, it'll roughly take twice as long.
Exactly. Now with the set approach for two-sum, we get that O(n), time complexity.
Okay.
But it does come with a trade-off, right? We need extra memory to actually store the set,
Right.
giving us a space complexity of O(n) as well.
So we're gaining speed but using more memory.
Exactly.
What about that other approach, the one that uses two pointers?
Ah, yeah. That's where things get really interesting. So with this approach, we first need to sort the array. Then we're going to position one pointer at the beginning and the other at the end of the array.
Okay, I'm visualizing it.
Okay.
So we got our two pointers at either end of the array. What happens next?
So what we do is we calculate the sum of the values pointed to by our two pointers.
Okay,
And if it equals our target, bam, we found our pair.
great.
Now, if the sum is less than the target, we nudge the left pointer one step to the right. And if it's greater, we move the right pointer one step to the left.
So we're constantly adjusting which way the pointers are moving based on if our current sum is too low or too high.
You got it. And so this method has a time complexity of O(1 log because of that initial sorting step. But the beauty is it only requires constant additional space, O(1).
So if memory usage is a concern, the two-pointer method might be the way to go, even if it's a little bit slower.
Exactly. It's all about choosing the right tool for the job, considering both time and space constraints.
That's a great point. The two-pointer approach is really quite clever.
Yeah.
It just makes you realize that there's more than one way to solve these problems, and sometimes you just got to be clever.
Now, if we want to crank up the complexity a little bit, we can look at the three-sum problem.
Threesome. So instead of finding two numbers that add up to a target, we're looking for three numbers that sum to zero.
Precisely. And you might be surprised to learn that we can adapt our two-pointer technique to tackle this problem as well. But before we get into that, Let's shift gears and explore how two-pointers can help us navigate the, well, I guess you could say fascinating world of linked lists.
Linked lists, they always make me think of these like long chains of data all linked together. How can two-pointers help us with those?
Oh, they can be quite handy.
Okay.
One common task is finding the middle node of a linked list.
Yeah.
And the two-pointer approach gives us a really, really elegant solution.
Okay. I remember reading about this one. It was something about a slow pointer and a fast pointer, right? It sounds kind of like a race.
It does, doesn't it?
Yeah.
Just imagine two runners on a track. One's taking slow, steady steps, the other one's sprinting ahead. That's essentially how our pointers are working in this scenario. So the slow pointer will move one node at a time, while that fast pointer is zipping ahead 2 nodes at a time.
Okay, so I'm picturing it, but how does that help us find the middle one?
So think about what happens as they're going through this list.
Okay.
When the fast pointer reaches the end, that slow pointer, because it was going slower, will have only covered half the distance.
Ah, I see. So they're like perfectly synchronized. The slow pointer's right in the middle when the fast pointer hits the end.
Exactly. And it all happens in one pass through the linked list, which is really efficient.
Yeah. Now, let's say we want to reverse a linked list. This might seem like a tricky maneuver, but our two pointers are up for the challenge.
Reversing a linked list, that sounds pretty complicated.
Yeah.
How do we even start that with two pointers?
So the key here is to think about it step by step.
Okay.
Instead of trying to flip the entire list at once,
Yeah.
we're going to use our pointers to detach each node and reattach it in the reverse direction.
So it's like we're carefully taking it apart and then putting it back together in reverse order.
That's a great analogy. So we start with a pointer at the head of the list and another one pointing to null. Then for each node, we just adjust the pointers to essentially redirect the links.
So it's like performing surgery on the linked list.
Yeah, it's very delicate.
I can see how making these small changes with the pointers can lead to a big change in the overall structure.
Right. It's really quite ingenious.
Yeah. While we're on the topic of linked lists, I remember another interesting application, which is checking for palindromes.
How do two pointers help us determine if a linked list reads the same backwards as it does forwards?
Palindromes. They do have a certain elegance to them.
Yeah.
And with two pointers, we can efficiently check if a linked list has that symmetrical quality, right? So remember our slow and fast pointers from before. We're going to use those again to find the middle of the linked list.
Right, that trusty technique.
Oh.
So we find the middle node, and then what?
Then we perform another clever maneuver. We reverse the second half of the linked list, starting from that middle node.
Interesting. So we have two halves now, one the reverse of the other?
Precisely. And now comes the final step. We just compare these two halves element by element.
Okay.
And if they all match up, boom, we know we have a palindrome. If we find any mismatch, we can conclude that it's not.
It's like we're holding up a mirror to the linked list.
Yeah.
If the reflection is identical, we got ourselves a palindrome.
You got it.
I love how we can break down a complex problem like that into manageable steps.
It is quite elegant. Now, even though we're talking about two pointers, I think it's worth mentioning that this technique is also used within larger algorithms as well.
Right.
So, for instance, sorting algorithms like quicksort and merge sort actually rely on two pointers for specific tasks.
Really? I know those are really efficient sorting algorithms, but I never knew two pointers were part of it.
Oh, yeah, absolutely. In quicksort, two pointers are used to partition the array around a pivot element. So they're working together, making sure that elements smaller than the pivot end up on one side and the larger ones end up on the other.
So they're basically working together to organize the data.
Exactly. And then in merge sort, two pointers play a crucial role during the merging process, helping to combine two sorted subarrays into a single sorted array.
Wow. It's just fascinating to me to see how this really simple technique shows up in so many different areas of algorithm design. I mean, it's a testament to its power and versatility. Speaking of versatility, I remember that we were going to discuss how two pointers can help us detect cycles in linked lists. Now, that one really piqued my curiosity.
Ah, yes. Cycle detection. It's a classic problem, but it has a very, very elegant solution using, you guessed it, two pointers.
Okay.
But before we dive into cycle detection, let's just take a moment to appreciate how beautiful and efficient this two-pointer technique is.
Yeah, it really is remarkable how much we can do with just two well-placed pointers, right? I mean, they help us move through these complex data structures, streamline these algorithms, solve problems in ways that I don't know, it would be much more complicated otherwise.
Absolutely. And the best part is this technique isn't limited to what we've talked about today.
Right.
It can be applied to a whole range of scenarios, from string manipulation to graph traversal. You can even use it in image processing.
Wow. So mastering this technique just opens up a whole world of possibilities for algorithm design. It's like having a secret weapon in your coding toolkit.
Exactly. Now, are you ready to unravel the mystery of cycle detection in linked lists?
Absolutely. Let's dive in. Okay, so cycles in linked lists. Imagine a linked list that instead of like ending neatly, one of the nodes points back to an earlier node, creating this loop.
Right.
How on earth do we detect something like that?
It can seem pretty complicated, but it's actually a pretty intuitive solution.
Okay.
You ready for this? Remember our tortoise and hare? The slow and fast pointer?
Yeah.
They're back! They're going to race again on our linked list track.
Okay, I'm picturing them at the starting node. What happens next?
Well, if there's no cycle, the hare obviously is going to reach the end of the linked list, right? Because it's moving 2 nodes at a time.
Makes sense.
Now, what if there is a cycle?
Oh, okay. Yeah, what happens then?
This is where things get interesting. If there's a cycle, that hare, zipping around that loop, is eventually going to catch up to the tortoise, who's just plodding along 1 step at a time.
So they're going to meet somewhere in the cycle.
Exactly. That's how we know there's a cycle. It's like, imagine 2 hikers taking different paths in the woods,
Okay.
and they end up bumping into each other. Well, that means they must be on the same path, right? Not separate paths.
Okay.
So it's the same idea here.
That's a great analogy.
Yeah. Now, let's say we want to know more than just if there's a cycle. What if we want to know exactly where that cycle starts?
Okay, yeah. How would we do that?
Well, there's a clever extension to this technique.
Okay.
Once our hare and tortoise meet,
Yeah.
we send that hare right back to the beginning of the linked list,
Yeah.
and then both pointers move 1 step at a time.
Okay.
The point where they meet again, that's the start of our cycle.
Oh, wow, that's so clever.
It is, right?
It's like they're going back to figure out exactly where they went wrong, where that loop started.
Exactly.
So we've seen this 2-pointer technique in arrays, in linked lists, even in sorting algorithms,
Yeah.
and now cycle detection too.
Yeah.
Is there anything these pointers can't do?
Well, I don't know about everything, but it's a really versatile tool, that's for sure.
Yeah.
And every programmer should know how to use it. And the nice thing is, it's not just about efficiency.
Right.
It often leads to cleaner code that's much easier to understand.
Definitely. It's much nicer to look at code like that.
So to all our listeners out there, I really encourage you to just try this technique out, play around with it,
Yeah.
try implementing the examples that we've talked about today,
Right.
and then see if you can apply it to other problems that you come across.
Yeah.
You might be surprised how often those 2 pointers can really simplify things.
It's like having a whole new way of looking at how to solve problems.
Mm-hmm.
Once you start thinking with 2-pointers, the possibilities are kind of endless.
Mm.
You might even discover a whole new application that nobody's even thought of before.
Exactly. That's what's so exciting about algorithm design. There's always more to explore,
Always more.
But for now, this is the end of our deep dive into the world of 2 pointers.
Okay.
And we hope you learned something new today.
And that's a wrap for today. So we really hope you enjoyed this deep dive into 2-pointers.
Mhm.
And until next time, keep those algorithms sharp and those pointers moving and those minds curious. So cycles in linked lists. Imagine a linked list that, well, instead of ending normally, one of the nodes points back to an earlier node, creating a loop.
Right, right.
How do we even detect something like that?
Well, might seem a little complicated at first, but the solution is surprisingly intuitive, I think.
Okay.
You ready for this? Remember our analogy of the slow and fast pointers, the tortoise and the hare?
Oh, yeah, I remember that.
They're back. Another race, this time on our linked list track.
Okay, I'm picturing it. They're all lined up at the starting node.
Mm.
What happens next?
So if there's no cycle, the hare is eventually going to reach the end.
Right. Makes sense.
Yeah, because it's going faster.
Exactly.
Yeah.
Now, what if there is a cycle?
What happens to our racers then?
Well, this is where it gets interesting. If there's a cycle, that hare, zipping around, is eventually going to catch up to the tortoise. Wait, so they'll meet somewhere inside the cycle?
Exactly. That's how we know there's a cycle.
Wow.
It's like, imagine 2 hikers, right, taking different paths in a forest.
Okay.
And they bump into each other. Well, that means they must be on the same path, right?
Right. Not separate trails.
Exactly. Same idea here.
I like that. That's a good analogy.
Now, let's say we want to know more than just if there's a cycle.
Yeah.
What if we want to know exactly where it starts?
How would we do that?
Well, there's an extension to the technique.
Okay.
Once the hare and the tortoise meet, we reset the hare back to the beginning of the list.
Okay.
Now, both pointers move one step at a time.
Mm-hmm.
The place where they meet again, that's the start of the cycle.
Oh, wow.
Yeah.
It's like they're retracing their steps to find where that loop started.
Exactly.
We've seen the two-pointer technique with arrays, linked lists, sorting algorithms, cycle detection. Is there anything these pointers can't do?
Well, they're a pretty versatile tool, that's for sure. I think every programmer should have this in their toolkit.
Yeah, it's so useful.
And the beauty is it's not just about efficiency, right?
Yeah.
It often leads to cleaner code that's easier to understand.
Definitely.
So to all our listeners, I encourage you to experiment with this technique.
Yeah, get out there and play with it.
Try implementing these examples that we talked about today,
Mm,
and then see if you can use it on other problems that you come across.
right.
You might be surprised how often this can really simplify your solutions.
It's like having a whole new way of thinking about how to solve a problem.
Yeah, exactly. Once you start thinking with 2 pointers, well, there's no telling what you can do. You might even come up with some new application that nobody's thought of before.
It's true. It's really exciting.
It is.
Well, that brings us to the end of our deep dive into the world of two-pointers. We hope you enjoyed it and maybe learned a thing or two along the way.
Yeah, we had fun.
That's a wrap for today's deep dive. We hope you enjoyed it. Until next time, keep those algorithms sharp, those pointers moving, and those minds curious.